Hello, this is Dr. Christy Patton-Lukes, your professor for Chemical Engineering 3111. In Lab 3, we'll be continuing our examination of ways to find roots of nonlinear equations. And today we're going to be looking at fluid flow. And so the first thing we need to know about fluid flow is the Reynolds number. Whenever we have flow in a tube or a pipe, we characterize this based on a dimensionless quantity called the Reynolds number, which is the diameter times the viscosity, or velocity, excuse me, times the density, divided by the viscosity. And the diameter would be in, say, meters, the velocity in meters per second. Density would be in, say, kilograms per cubic meter, and the viscosity would be in kilograms per meter per second. And when you work with those units, then all the units will cancel out, and this thing has no units, hence being a dimensionless number. And the Reynolds number is useful for a lot of our problems that we'll be solving in the future. But for today, we're looking at flow in a tube. And so we're going to be looking at flow through a simple tube. But what we want to do is we want to characterize what is the friction factor, how much frictional loss is there as the water flows through this tube. And there are many ways of doing this. We're going to be working with the fanning friction factor. And a formula that can be used to calculate this is the Reynolds equation, which says that 1 over the square root of F, the friction factor, is 4 times the log base 10 of the Reynolds number times the square root of F minus 0.4. And then we use the friction factor in other calculations, such as estimating pressure drop along a length of pipe, which tells us things like how big a pump I would need in order to move the material from one location to another. And so this is an important quantity to know. So we're going to be looking at solving this. Now, there is a chart that is very useful, which is the Darcy friction factor. The Moody diagram shows the Darcy friction factor, which is read on this scale over on the left side, as a function of Reynolds number and roughness. So each one of these lines is for relative roughness. The equation we're using is for this bold line here, which is for a smooth tube, okay? And we'll assume that our tube is relatively smooth. Now, the Darcy friction factor is 4 times the fanning friction factor. So whatever value you read off of here, divide by 4 to estimate the fanning friction factor. Now, the reason I tell you this is because this gives us a graphical estimate of what our answer should be from the other equation. So in today's activity, what we're going to do is estimate the friction factor for the flow through this plastic tube. And I'm doing it using a submersible pump. So these are something that you get at a store. I have a water fountain out front of my house. And so this is the sort of pump that you would use for that. And I have this set so that it's on a low flow rate. It can go up to 140 gallons per hour, okay? But that's the maximum setting, and I have it at much lower, and that's at a height of 1 foot because the elevation you raise the water to makes a difference. The tube will go in here, and then I will submerge this in a bucket of water, keeping the electrical cord dry, and I'll attach this to the bottom of the bucket, and then I'm going to have the water flow through this tube back into the bucket, or I'm going to be, while we are timing this to get a flow rate, I'm going to be flowing into this graduated cylinder. So we're going to use a stopwatch and a graduated cylinder to estimate the flow rate. And I am going to need the diameter of this tube, and the tube is says that it is a 3/8 inch inside diameter and a 1/2 inch outside diameter. The 3/8 inch inside diameter is the one that we're interested in because the flow is on the inside of the tube. So I'm going to show you this experiment in a separate video, but we're going to be getting a mass flow rate of water through this tube. You will be able to calculate the cross-sectional area of the tube, and we're going to use that to estimate the friction factor. So we're going to do this assuming that the temperature is roughly 20 degrees C. I am indoors, so that's not too far off. At 20 degrees C, the density of water is 998.2 kilograms per cubic meter, and the dynamic viscosity, mu, for the water is 1.002 times 10 to the minus 3 kilograms per meter per second. And we're going to use those numbers to calculate the Reynolds number after I've got the flow rate. And then we're going to use the Reynolds number to estimate the fanning friction factor. Now I want you to do this using the secant method and successive substitution. You'll need to use graphing to get a reasonable first guess for these methods. And so therefore you have the Moody chart for that. But remember that that's going to get you an answer that then you're going to divide by 4 to get your real first estimate. I want you to report the fanning friction factor to 4 significant figures. Upload your Excel file that includes the VBA code, and then do the successive substitution just in Excel. You don't need to have VBA code for that. All right, so that concludes this video. Remember, there is a second video where I actually do the experiment. See you in that one. Thank you.